Hello everyone, this is the first talk in this room, and here we have Giovanni Bajo. Giovanni Bajo is the CTO of at Develer. Develer is the company that organized the GoLab. Giovanni will talk to us about the Go race detector, and so let's start.
Okay, so this is an introductory talk about the Go race detector, just to show you what we can do with the race detector, how it can be useful for Go programmers, and how to use it. This is just a short slide about myself. I've been a C++ programmer. I worked in the embedded fields, also writing firmwares. Then I moved to Python in 2003. I've been a Python programmer for many years, and in the last 4 years, I discovered Go. I've been following development of Go in the last years. I introduced Go in the company, and we have begun making production work with Go, and we are very happy with the results. So this talk is about race conditions, which are globally called Heisenbugs on internet. This is a portmanteau, is like a joke of words between Heisenberg and bugs. So if you know the uncertainty principle of Heisenberg, it says that things change as you look at them. So basically, a race bug is usually a bug that you don't always reproduce. It doesn't always manifest itself in the same way. So basically, you need to pay close attention to such bugs. So you know that sometimes programmers just pretend it didn't happen and just try to get over. And because these bugs are usually very hard to debug, right? In different programming languages, it's not very easy to debug them. Usually there are a lack of tools. So there is, of course, people study in universities and after how to handle race condition with mutex, logs, and everything. But when something is wrong in the code, it's really hard to detect it. You just basically see the bug, and you just try to understand what's going on by staring at the code. It's usually not very easy to actually spot the bug. So what Go offers is actually, in the runtime, is got a feature that you can optionally enable while you compile the code to turn on the race detector, and that will help you spot the bugs. To understand better why we need the race detector, we need to briefly discuss about the Go memory model. If you have been doing some Go programming, I think it's clear that when you have multiple Go routines running, they share the same global memory. Okay, so this is the basic memory model, which is the same in Python, in C++. So you have like a shared global memory, and you need to protect yourself. So usually what people say is, of course, use channels to communicate between Go routines. That is the standard. But sometimes sometimes the code is just better if you don't use channels. Actually, channels are like the main communication protocol between Go routines. So they are really nice when there is like a pipeline of stuff, like worker, consumers. But sometimes you just need to have like a shared state somewhere. And when you have a shared state, you need to defend yourself from race conditions. So if you go to the actually guide about the Go memory model that you find on the official Go website, it basically it's got a really short introduction, because describing a memory model in a programming language is a complex task. Actually, you need to be very specific about details on how the compilers rearrange the code. So they put an introduction in front that we just try to summarize, like in one word, the memory model. So I just say that programs that modify data being simultaneously accessed by multiple Go routines must realize success. So this is just a very short statement. And then there is a big document. In fact, the introduction goes on like this. If you must read the rest of this document to understand the behavior of your program, you are being too clever. And in fact, don't be clever. Okay, so try to keep it easy. Just visualize yourself, your code, like accessing at the same times. You need to defend yourself. So this is just a short example. So we will dive into code. This is a short example. I will describe it. I'm just writing a simple TCP server. Okay, so not HTTP, but just TCP server which can handle concurrent accesses. And I will introduce some sharded state. In this case, the sharded state will be the number of clients that have made a successful connection to the server, okay? So I have a server class, which is a net.listener, and the number of clients variable holding it. This is just a constructor, so I'm just listening on the specified protocol and address, and returning the server object, the server instance. This is just basic TCP server stuff. I have a serve function, which is looping forever and accepting connection from the TCP socket. And then I'm spawning a Go routine to handle each client. This is just standard design for TCP servers. And before spawning the Go routines, I'm incrementing the number of clients to just bookkeep how many clients are connected to my server. There is just a shutdown function. And this is the handle client function that handles a single client. So the only thing it does is just write to the client connection this string, hi, your client number X that connects to me, and then close the connection, okay? So it's really simple. And this is just the main, okay? Of course, this could be like an initial attempt at writing it correctly. It's not correct, of course, but we've put the increment before spawning the Go routine. So one could say, like I put it before, so there is no race condition, like if you don't have like a clear picture in your mind of what's going on. But of course, there are race conditions here, because you could have multiple clients concurrently opening a connection, and so you could have a race condition here. The point is that even if this function, the serve function, is executed by a single Go routine, so you increment here and then spawn a client, of course there could be a race between the next client connecting to the server and this access to the variable, okay? So that is the race condition. And we can have a look at it. So I hope it can be read, otherwise I will increase the font a little bit. So this is just the, oops, sorry. Okay, this is just the program we just saw, okay? So I will run it. Okay, and here I will attempt a connection. Okay, so I'm connecting with Telnet. Can you read the text, right? I'm connecting with Telnet to the TCP port. The connection is successful. And then I get the message back from the server, hi, your client number 1 that connects to me, and then the connection is closed, okay? If I attempt it again, everything appears to work, right? Because I'm sequentially connecting to the server. I cannot be fast enough, of course, to trigger any problem. So everything seems to work here. So how do you see a problem in production? This will be a very tricky problem, because what will happen is that basically sometimes you will just miss one connection in your bookkeeping, right? So it's very hard to actually to realize there is a bug, right? Because you will just missing a few connection count. So how do you turn on the race detector in Go? You just need to add the dash race option to Go run. Let me put it on top. So just the dash race option. You can pass it to Go build or to Go run. It's the same. Just pass the dash race, and Go will turn on the race detector. So now the runtime is basically between 10 and 25, between 10 and 20 times slower than before. And it also uses between 10 and 20, actually between 5 and 10 more memory than before. So it's just for, of course, debugging environment, development environment. But what it does is basically it guards every shared memory access, trying to detect what's going on. So if we try now, I tried once and nothing happens because there was no race condition. Do you remember I said before that I'm not fast enough to trigger it, right? To trigger the actual bug. But if I run it twice, the race detector tells me that there is a potential race condition. So it tells me that there is a race condition. It says warning, data race. So it tells me what kind of race condition is it. It's a data race, and it tells me there was a write in the main Go routine, and it points me to the actual source code line where the variable was being written, and a previous read was made at a different line. So it tells me that a counter.go 37, there was a write, a counter.go 50, there was a read. So if we have a look at the code, let me find it. So 37 was written, and 50, it was read, okay? So it's basically telling me that there is, when did the race detector trigger? It did trigger when the second write was being performed. And it is telling me that the second write potentially races with the previous read, okay? With the read made by the previous TCP connection. So it's very useful in this case because it's not actually detecting a real race condition as it happens. It detects a potential race condition. So it's actually much more useful. You don't need to trigger the race condition in production for the race detector to trigger. You just need to run your code with the potential race condition in it, and the race detector will tell you, yeah, there is a potential race in this line between this and this line. And it also tells you where the Go routine was spawned, from which part of your code, okay? So another thing we can do is we can write a test, because then it's easier, of course, to trigger. Because also Go test accept the, sorry, of course, this. Also Go test accept the dash race option, okay? So I wrote a simple test. If we have a look at the code, it's just, sorry, it's too dark, but anyway. It's just, does 5 connections in a row sequentially, not parallelly, not in parallel, but sequentially. And then if I run it, everything works. If I run it with, I let it compile. OK, and the data race is triggered. And of course, when a data race is triggered because of the dash race option, the test will fail automatically, OK? So, OK, so of course, how can we fix this data race? There are a couple of options. The first option is to use a mutex. This is, of course, the slowest primitive, but it's also the most known. So we basically just guard the shared state access using a mutex. So we lock before and unlock after. In this case, I have a bug here. This should be NC. So let me describe this. Here, I'm locking the write, OK? And here, I'm just extracting the read in a single statement, guard it with the lock, and here I should use NC. Sorry for the mistake. I didn't put the lock around the whole statement. That will be, of course, the first option, because you see you had a read here, so you would just put the lock before and lock after. I'm not doing that because that will hold the lock much longer than necessary. It would hold the lock across the whole I/O access, I/O write. In this case, I just want to lock the shared state access, the memory read, and then I can do the I/O without holding the lock. So a different way of fixing the same bug is by using the atomic primitives. The atomic primitives are primitives implemented by CPUs that allow you to basically safely access the memory between different threads. This is how you do. Go exports a package in the standard library called sync/atomic, which exports all basic, most actually, atomic primitives. In this case, you need to basically switch to these functions. There are primitives for handling integers of different sizes and different, like signed and unsigned. So we are using atomic.addInt64 to increment a int64 variable. And then we are using loadInt64 to access the variable. In this case, there is no atomic type being used. The variable is a simple int64 variable. So you need to make sure that every time you access that variable, you are going through an atomic function. There are no helpers for this, not even GoVet complain about this. So you need to make sure that every time you access that variable, it goes through an atomic function. Otherwise, you still have a race condition in your code. But the Go race detector can help you, of course, especially when it's integrated in the test suite. So why this is better than Mutex? Mutex is something that is implemented at the operating system level, so it requires a kernel context switch, while Atomic are just CPU primitives. So they're just CPU opcodes that basically internally lock the CPU so that if you have multiple cores, they basically make sure that there are no two cores accessing at the same time the same cache line, of course, because the CPU is always accessing cache lines. If you can read a little assembly, this is the implementation in Go of the add unsigned integer 64 function. So basically, this is the point where they are using this lock add function. With this lock prefix is basically triggering the atomic functionality. It's, of course, much slower than the single add opcode, but it's still an order of magnitude faster than doing a full kernel context switch and back to the user space. If we go through this file, this is the atomic AMD64 implementation. We can also get to the load function, the one that we were using before to read the memory. And this is the implementation of the load function, which is basically just reading from the memory. This is basically just reading from the memory because in the AMD64, basically each memory access, word memory access is already atomic by itself, so it cannot clash. So basically, when you load atomically, you are basically just reading the memory, okay? But I told you before that you still need to put atomic in the source code. So if you don't put it, you still get a race condition. So how can the race detector detect that there is a race condition if you're just loading the memory like you would do without atomic? This is a little weird, right? So basically, there is actually a little trick, is that there is a different source code for the race detector. So when you're using atomic with the race detector, there is a different source code because there is this build tag that you can use to differentiate between code being run under the race detector or being run without the race detector. It's also useful for tests because sometimes your tests with the race detector are too long, so you want to disable a few of them when you are turning on the race detector. So they have a different implementation so that they can help you putting all the loading places for compatibility for different processors where atomic loads need to be implemented with the real different opcode. Okay, let me just drink a little bit more. Okay, there are a couple of more common races I wanted to show you. This one is very, very common. So in this case, the shared state is a map, and the map in Go doesn't allow for concurrent read-write accesses. So you can have concurrent read accesses, but you cannot have a concurrent read and write accesses. So in this case, if you try source code like this, and then you have a Go routine registering a service, while another one look up for a service, you will get a race condition. And in this case, you need to put, basically, you need to put a mutex around it. It's the easiest option. If you go to GitHub, there are a few concurrent maps implementation, like they try to be more granular with locks and try to, with different tricks. Like if you split the map in different buckets, then you can lock only if there is access to the same bucket, so stuff like that. But most of the times, of course, just putting a mutex is enough, especially for this kind of stuff, which is probably not, how do you say, performance critical. And this one is also a very common example of a mistake. I think this is known by most Go programmers, also from Python programmers, is that when when you spawn a Go routine, the closure that capture here the loop iteration variable always capture the same variable. So basically, always go to the same position in memory. And this is probably not what you were thinking while writing the code. Actually, also GoLab detects this, so it's not really common right now. But the race detector, of course, will tell you that you're still accessing the same I variable, loop iteration variable from multiple Go routines. So in this case, the fix, of course, is to just pass the iteration variable to the function being spawned. OK. I have a few suggestions when to help you handle this kind of issues. The first one is to get very familiar with both the sync and sync atomic packages. They have many different options, especially the sync atomic packages also offers like compare and swap to implement lockless data structures, but they also offer something called atomic.value, which is where you can store a generic object and access it atomically between different Go routines. So this, you should probably take some time to read the documentation of sync and sync atomic and make sure you understand the options you have at least, so that when you write the code, you can get back and try to implement them. Sometimes when you try to run the race detector across an existing user base, it's useful to stop on the first failure to help you like debugging. So the Go runtime exports this Go race environment variable where you can configure the race detector. This is one of the options, exit on failure equal to 1, which means what it says. There are also different options because by default the race detector outputs to the standard error. If you want to like redirect to a file or something like that, there are different options here that you can use. Can be useful to run tests with more structure. And as I said before, you can use a build tag to skip tests that are too slow. Sometimes you, for some reasons, there are single tests that takes really long time, like hours or many, many minutes, depending on the implementation. Like I had a test suite doing some sort of building packages on the file system using Circle CI as a CI engine. And like the normal test takes, I don't know, maybe 15 seconds. And if I turn on the race detector on that one, it takes like 7 minutes, 8 minutes or something. I'm not sure why that test specifically triggers some kind of behavior with the runtime. But anyway, the trick is just to skip the test when you turn on the race detector. And last thing is that the race detector currently is implemented only on AMD 64 architecture. So if you are targeting a different architecture, you probably want to make sure that your application, at least your test suite, is always running also on AMD 64, so that you can always run the test suite on your computer with the race detector, and then like deploy on ARM or whatever architecture you are targeting. Okay, it's done.
Time for questions now. Anyone? Someone want to?
So a bit technical question about the background. Vicino?
I hope I can answer.
When you say, okay, use a concurrent map, otherwise if you mutate a map from multiple Go routines, you risk a race. How bad is it? I mean, you risk a race, you risk a panic, you risk corrupted the data structure. Just to have an idea how careful is this line when you step out of what you should do.
This is a good question. You actually risk to corrupt the memory of your process. This is what you risk. It's actually very dangerous. And also Go programmers, Go maintainers are really picky about this. They always say that they don't want to give any kind of promise about the scope of what happens if you don't guard your memory correctly. But there is actually an interesting article by Intel about this. They try to show you that is like the risk of having a race condition of your code that doesn't just affect the portion of memory you are accessing. I can give you the reference to this paper.
Will you share this reference somewhere on the GoLab site or?
You mean from the Intel
yeah,
paper? Yeah, okay. I will put it on the slide, okay? I will add it to the slide so when we put them online, it will be there.
Great.
Anyone else? No? So thank you, Giovanni.
So